First, I'd like to thank the organizers for the invitation. I'm very glad to be here. And what I wanted to do today is to talk about abstraction. So I'm doing a PhD on the history of mathematics, but since it is history and philosophy, I propose to the organizer to talk about both history and kind of philosophy, talking about abstraction. Though I'm not going to talk about abstraction in general, but in a specific context, that is the development of Lattice Theory in the 30s. And more precisely, what I would like to do today is to link that practice of abstraction to some mathematics that were done in the 30s, which is Lattice Theory. So first, let's get rid of the mathematical formalism. I'm going to talk about lattices. And what is a lattice? It is a partially ordered set. So the set can be ordered by a relation, like if you take the natural numbers and you order them with one being greater than another, like 2 is greater than 1, you have an ordered set. And a partially ordered set means that not all the elements can be compared. So here I draw the lattice in a diagram form, the lattice of the divisors of 36. And as you can see, so the representation is that if I draw a line, like 4 is a divisor of 12. But you can see that 4 is not a divisor of 18, but 18 is not a divisor of 4, so they are not comparable. So the set is partially ordered. And so lattice is a partially ordered set in which two elements always have what's called the greatest lower bound and the least upper bound. So what are they? The thing is, if you take two elements, such as 9 and 6, they have, started with least upper bound. They have a least upper bound, which is an element that, in which there are divides it, so both 9 and 6 divides 18, and every element that both 9 and 6 divides is divisible by 18. So you see, 36 is divisible by 9 and 6, but 18 divides 36, okay? And in the same way, they have a greatest lower bound, which is the exact opposite. It is a number that divides both, and which is divisible by every element that divides both. Okay, so it may be a little bit trickier than that. For example, if you take, instead of 9 and 6, you take 9 and 2, the least upper bound is still 18 because they both divide it, and the greatest lower bound is 1. So it's just a little bit trickier. And you may also ask what happens if one of the two elements that I'm trying to deal with is a divisor of the other, such as 3 is a divisor of 9. Well, it's not a problem at all, because in that case, the least upper bound is just the greater of the two, and the greatest lower bound is the less of it. Okay? So there is another characterization of what a lattice is, and it's done with operations. A lattice is also a set of elements given by on which act two operations, which are basically just the fact of taking the greatest lower bound and the greatest lower bound and the least upper bound. Okay? And these operations satisfy a certain number of identities. Here I gave just 2 examples, which are idempotency and commutativity. It's another characterization that I'm going to use very quickly, so I just put that here. And these lattices is related to a theory of lattices. As you can see here, I just put 2 covers. Well, this one is a bit ugly because of the resolution. Here I put 2 treatises on the subject. So there is something called lattice theory. And that's what I'm going to deal with today. And my question is, obviously, what is the theory of lattices, and how can I study the history of that theory? So one answer would be, let's just take the definition of a theory to be what's in those treatises and try to do its history. And my claim is that by doing so, you have a definition of a theory before any historical inquiry, and in that way you have a very biased history in which you cannot really discuss what is the content or the boundaries, where it starts, or the important text that you should deal with, or even the aim, what is the aim of the theory. You cannot discuss that in your historical inquiry because it is given a priori. So for example, if you look at the main actors of the theory and you take this kind of definition of a theory, they are given before the inquiry, and you have sentences like this, one by George Grazer, which is the author of the second critique represented, and he said that it was Gareth Birkhoff who developed the theory. It is kind of the same point by Birkhoff himself, who says it was after his works and those of Stone and von Neumann that lattices became, well, to precisely applicability of lattices became very important, and I'm going to come back to that in the next slide. And it's the same in an historical book, this time by Leo Corey, who said that it was Birkhoff and Hall who were the main figures in lattice theory. But you also have the aim of the theory that is given, and here in those kind of books, the aim of the theory is to unify, like you can see in Grazer's citation, is to unify apparently unrelated domains of mathematics, which is linked to the applicability I was talking about. And it is the same in different texts. This one is also a mathematical text on lattices. And Birkhoff says his predecessors did not recognize the pervasiveness of lattices. In the same, in this philosophical article, the main point of lattice here is to be central in many mathematical fields. And so what I would like to do is to discuss that definition of a theory in order to make its history, claiming that the definition has an impact on that history, and that the results and objects and aim, etc., cannot be taken for granted before any inquiry. Okay, and so what I would like to do today is to take the example of abstraction to try to get it on what it means in a specific context of lattice theory in the 30s. To do so, I'm going to start with a discourse on mathematics that was given by Eric Templeman on the occasion of the 50th anniversary of the American Mathematical Society. So this talk was given at this anniversary.
Which is there?
I'm sorry?
Which is Bell?
Ben is not here.
He's taking the photograph.
Taking the photograph. But yeah, I wanted to have the Columbia University and not just the garden, so Ben is not here. So it was in 1938 that the American Mathematical Society is celebrating its 50th birthday, and it is a huge moment of celebration. A lot of things are organized for this anniversary, and what is described as the main feature of the meeting is a series of talks given by several mathematicians with 2 general addresses given on American mathematics, and then 8 addresses that reviewed different domains and gave important directions. I just list quite a few examples. So these 2 are the general ones, and then you can specific content, so dirichlet problems, calculus operations, and the one I'm interested in is Eric Bell's 50 years of algebra in America. Because of the context of the talk today, I should say that America is always, here is always United States. Sometimes Canada, but that's it. Ben is actually the only one saying, well, America is also South America, and thing is, he's just saying that to say, well, but they are not interested in algebra, so I'm not going to talk about that. So, well, it's pretty much United States mathematics. So I'm going to talk about Eric Bell's address for two reasons. First, he talks a lot about abstraction, really focus on abstraction. Secondly, abstraction to him is really related to abstract algebra, which is lattice theory, but it is both relevant in both ways. So what Bell is saying about abstraction is that is that it is responsible for the development of mathematics, and he's putting it that way. He said that he cannot talk about all algebra because there is too much material, so he will, and that's starting here, he will only focus on the broader aspects of the rapid growth from the age of relative algebraic innocence, when everything was special and detailed, to our present highly sophisticated abstraction. So what I would like to highlight is that abstraction is, well, highly sophisticated, but it's also present as opposed to the algebraic innocence, where when everything was special and detailed. So abstraction here is opposed to the past and is opposed to the particular. And this, he keeps going on with that. As you can see here, abstract algebra that he has inside has been obscured in a welter of particulars. So abstraction to Bell is opposed to that particularities. And of course, because of the context of the talk, he is also saying that this kind of abstraction is kind of an American feature. Okay, so here he's also proposing abstraction to practical mathematics, such as solution of equations for engineering or mathematical physics, but he's saying that no, if anything, algebra in America showed a tendency to abstractness considerably earlier than elsewhere. So abstraction is both opposed to practical and is an American feature. Okay, and just to qualify a bit what I've just said, he's not focusing only on abstraction, but he's saying, well, of course, abstract has to rely on something concrete. And here he's just saying that abstract algebra cannot root an operation on absolute vacuum. Okay, so it has to be based on something. So it's not only about abstraction, and the concrete also has a role to play. Okay, just to sum up, abstraction has been presented by Bell as a driving force and motivation that is going to abstract algebra, which is the present and highly sophisticated mathematics, but is responsible for both historical development and mathematical development, and these are intertwined, and is opposed to, well, mostly particular, but also practical and everything. Okay, and so what he has in sight is this abstract algebra that is opposed to him to linear algebra, and there is something that is developing right now to him that is called modern algebra, and that represents the best abstraction. So it is a new school, we would say, a vigorous young school who do cultivate the subject, and that is very prolific. And he is comparing this new abstract algebra to something that has a huge impact on American mathematics at the beginning of the 20th century, that is theory of groups. And so he's saying, well, not much has been done, but there is something that is going on that will be huge. So this is, to him, this is the important mathematics. It's what has to be done in the following years. And the subject is presenting, in fact, as algebra par excellence. And what is interesting to me is that when he describes the subject, it is not what we would call today abstract algebra, because he has inside only lattice theory. And he's presenting only lattice theory, and there is nothing else in his presentation. So there are two main contributors, the one we've seen before, Oysten-Orr and Gerhard Birkhoff, who developed two theories. Oysten-Orr to the foundation of abstract algebra on structures of lattices, and an abstract theory of lattices done by Guy Decaens. And he said that it may be anticipated that there will be no dearth of attractive abstract theorems unifying numerous particulars of current theories. So again, abstraction is linked here to unification.
So when you speak about the abstract theory of lattices, you mean axiomatization of lattice theory by the property of the relation of Meek and John? That's what you mean? In which sense there is an abstract theory of lattices and a non-abstract theory of lattices?
Well, that's a very good question. And I'm going to come back to that in a few slides. No, I'm not talking only about an axiomatization, because people using lattices without axiomatization, but I don't know if there is any, but if someone would do that, I should put that into lattice theory because they use lattice. But I'm going to come back to that in a moment. Okay, so now I have kind of a definition of abstraction, which is that the definition, the theorems and examples that you can find in mathematics are not valid only for a class of specified objects, but also for objects having similarities. And this implies that particular theorems on this specific object are nothing more than instances of a more general trend. And with that definition, I can, I don't know how much time I have left.
Empezó a las 10 de la mañana.
Disons, il y a 20 minutes de 40. Voilà. Donc, s'il faut la discussion, il reste 10 minutes.
Okay, okay, fine, thank you. So I can go on with lattice theory, in which I'm going to answer the question. And to study this abstraction in the context of lattice theory, I constituted a corpus on which I would have a lot to say, but I don't have time. That is based on the bulletin of the American Mathematical Society, who published abstract of papers. So I took this abstract from 1933 to 1940, and I took the abstract mentioned in lattices or structures, that is the term used by Orr, and then the publication resulting of this abstract and the publication day 6. And now I can try to give a definition of a theory based on this corpus. And what I would like to do is not to give a definition like this, but to give characteristic components that are being part of this theory, that are being stacked in this theory. So at first there is this division between theory and application. There is the use of axioms, and all these components will take part and is intertwined in the development of the theory. The last one I put here is abstraction, and that's the one I would like to discuss. So for example, if I take the division between theory and application, and I look at Birkhoff's first paper of 1933, you see here that there is 5 parts. The 4 first one being theoretical, as opposed to the last one, which is applications. Okay? And what is the difference between these two groups is that if you look at the last one, so I'm starting with the applications, here are 2 lattices that are defined. And this lattice is a lattice of well-defined objects. It is a lattice of subgroups of a group. It is the exact same with this one. The lattice, you see, consider the family of linear manifolds in Cartesian n space, etc., etc. They evidently constitute a lattice. So a lattice here is something constituted by linear manifolds. And as opposed to these lattices of concrete objects, here we have a definition of a lattice in the first part, and there are lattices of elements, unspecified elements. And then, if you want to prove theorems in the applied part, well, you just prove them in the theoretical part. Here you have elements. Whoops. you have elements, and you can, for example, combine them with the operation I gave before. So you took two elements and you combine them with, for example, join. You can do a lot of these combinations. And you can, because they respect identities, you can identify some of them. So this is the identity of commutativity I gave before. These are the same elements. And so you end up with a lattice of 28 elements. Okay? This is a theoretical part in which the elements of the lattice are unspecified. And then you have just this application on the lattice of linear manifolds I talked about before. You see, the number of linear manifolds which can be constructed by successive projections and intersections from 3 given manifolds has 28 as its maximum values. And this is just because in the theoretical part you have this result as it abstracts. Okay, and what I would like to highlight is that this is not specific to Birkhoff, but if you look at other papers such as this one of Sanders McLean, this division between the lattices of unspecified elements and specified, well-defined elements is also relevant. So here you can see that you have lattices of field. You see in the field case. You construct a lattice of fields, and then in this sentence you see, for lattices, we state a corresponding exchange axiom. And this time, the axiom is on unspecified elements. So it's the exact same dynamic in which you translate axioms from a specific context to an abstract context in which the element is unspecified. And it is the same thing, for example, in that geometrical context. You see here, a lattice is set of unspecified elements, and then you have the projective geometry that is the lattice of all linear subsets, etc., etc. Okay, so there is an opposition between lattices of undefined elements and lattices of specified objects. And the purpose of this division, the purpose of this abstraction is, as you can see here, to relate together apparently different domains. So here you see projective geometry through lattice theory is correlated to Boolean algebras, fields of concepts, system of normal subgroups, etc., etc. And it is the same thing in this paper, in which you see that there are different domains of abstract algebra, and these domains have relationship and similarity, and he said that, or says that, it is natural to expect that these results may be derived from a common source, so lattices provide a common ground to study these different domains. And this theory division applications is based on axioms. And here, what I want you to highlight, I think I have time to finish this part. What I want you to highlight is that the axioms in the abstract theory, they are the part that allow to state results in an abstract form, but they are based on applications. So here, as you can see, Paul said that in most algebraic theories, we are interested in more special structures with simpler properties. And he said that, well, for instance, the normal groups are interesting, or the ideas in rings are interesting, more than just subgroups or just subgroups. And this is the fact that these sublattices are interesting that make him consider an axiom satisfied by these precise sublattices. And so it is because of this application that he's considering a specific axiom that is satisfied by these lattices. He ends up with the Decaens axiom, which is also called modular axiom. And a phenomena that is at stake is that this axiom became interesting in itself. So it is not related anymore to these applications, but is interesting in itself. As you can see here in the paper of Wilcox, he's trying to extend the modular axiom, which is the Decaens axiom, to other lattices that does not verify it. And it is so important that even other author that does not consider it, like MacLean, sorry, they consider it even though it is not verified in the lattice they are studying. You can see here it says the Dedekind axiom itself could not apply to the lattices of fields he's considering, but he's devoting 2 paragraphs to prove that it is not verified. It is the exact same for one and the other. It also shaped the theory in the sense that it defined an area to study, the area being precisely the lattices that verify this axiom. Okay, so the axiom substantiate this abstraction. They are the way through we can study abstraction, abstract lattices, and also become a proper object of investigation and give shape to the theory. Okay, just a quick word to conclude. On abstraction, so this abstraction relies on the theory and application division, theory being the abstract form of these applications. It relies on axioms through which we can substantiate abstraction, and is a worthwhile value as we have seen in Bell's talk. So it is a fight we should do to go for abstraction. Well, and on the more general aspect of what the theory and how should we define it to study its history, well, I get all these elements, and I think all take part in this definition, all are worthwhile studying to understand the dynamics of the theory. And I wanted to emphasize that we cannot take for granted neither the aim or the important object of the theory before our empirical study. Also, we cannot take for granted any given corpus that should be obvious to study the theory. And, well, this point I said it already, and it is not on, I would like to argue that theory is not only about these definitions and results that we find in books or treatises on the subject. Okay, thank you very much.